Have clicked on this video, I assume you have a slight knowledge about electronics, but most importantly about operational amplifiers, or op-amps for the record. These tiny little guys are the access stone to all of analog electronics due to their multiple uses in signal processing, filtering, and amplification, which is pretty cool. And if my assumptions are correct, I know you have done your simulations, make up your calculus, setting everything on the breadboard, and then, well, that doesn't usually happen. But something worse, that your voltages and currents do not match the ones you actually calculated. But how could this be? Did math lie to me? What? No, of course not. I mean, yes, but not the way you think of it. Turns out, the reason why your calculations don't match your results is because you made those calculations in the magical world of idealities, which unfortunately you're not a citizen of. During the designing and the fabrication process, the integrated circuits manufacturers actually know that their product may have some flaws or some sort of limitation. Fortunately for you, they actually inform you of these limitations in an incredible document called the datasheet. So basically they don't lie to you, you lie to yourself given the fact that you don't read the datasheet and you don't know what output voltage swing mean. Luckily for you, I do know what does that mean. So today I will be explaining to you some of the electrical characteristics of operational amplifiers. More specifically, I'm going to talk about the LM741. Let's start with the easy and obvious ones, so you heat up for the following characteristics. First of all, we have power consumption and supply currents. Well, what does this mean? This is just the amount of power you need to, turn it on. And yeah, that's it. That's about it. Here, let me show you. Here, I set up a circuit so that you can see how much current does the op-amp requires. In this case, you can see that the current is about
1.4 milliamps,
while the one on the datasheet is actually between 1.7 and 2.8 milliamps. We have operation temperature, which, as its name says, it's just the temperature needed for the circuit to work normally. This is usually not so looked after since it's not common to work with an LM741 in an environment which more than 125 degrees Celsius without dying to overheating. However, what if I tell you this? Let's say that it is your job to make something as ridiculously hot as a volcano thermometer. That thing is absurdly hot. So I don't think you should use the LM741 for this application. Next of all, we have supply voltage. This is a range of voltages you can feed your LM741 without blowing it up, or at least extending its useful life a little bit more. So there you go, kids, don't feed your LM741 with more than, 22 volts or else. Now that we have moved from the obvious ones, imagine this situation. Set up a comparator configuration. You feed it 5 and minus 5 volts and input some signals. If the difference between the inverting and non-inverting input signals is positive, the output voltage will go up to the positive supply voltage, since the amplifier has an infinite voltage gain. Normal, right? Well, it is not. There's at least two lies in that sentence. First of all, operational amplifiers do not have an infinite voltage gain. That's just one of the lies evil physicists tell you so that their calculations are easier to make. Fun fact that doesn't have anything to do with the video. Did you know that the first non-trivial solution to the Einstein's fields equation was made using a universe with only one object? That's pretty far off reality. However, with operational amplifiers, things are not so far away from what it actually happened. The voltage gain of an LM741 is about 200,000 volts per volt, which means you can get this much voltage using a single volt. That in that case, you feed your operational amplifier with 200 kilovolts, which we already know what happens. This is not that much of a problem, except if you're working with small signals. Imagine this situation. Most of the human body electric signals come around the order of the 10 microvolts, and that's a lot. So let's say you need to amplify one of those. It's not so easy anymore, right? Because if you plug in these signals into the LM741 without any configuration, you might only get about 2 volts by much. Another by lie in that sentence was that the voltage did go up to the supply voltages. And guess what? That doesn't happen either. Turns out the output voltage can only go so high, but can actually get to the supply voltages. Which means there's a tiny bit of information, which is not so tiny actually, that gets lost. What's the solution? Just crank the supply voltages up. Well, if possible, because something similar happens with the input voltages. The LM741 can only perceive entering signals to a certain point. What does this mean, actually? If you want to plug in a 6-volt signal into a 6-volt fed operational amplifier, the operational amplifier will not recognize this signal complete. We only recognize something about 5.994 volts, which is very close. But again, small signals do exist. What I just mentioned to you is called output voltage swing and input voltage swing, in case you were curious. If we keep reading our datasheet, we're going to stumble upon a parameter that's called PSRR. Yeah! What is that? Why is it in decibels? PSRR stands for Power Supply Rejection Radio. But what does this mean? Usually the DC voltages we use to supply our amplificators are not actually that much of a DC current, which means there are variations at the output voltage too. Fortunately for you, the LM741 got your back. The ratio of the variation of the supply voltage compared to that one of the output voltage, it's absolutely massive. So if the supply voltage vary around, 100 millivolts, the output voltage will only vary around 10 microvolts, as much. And if you want to know what does that 90 decibels mean in the datasheet, well, you just have to solve this equation, which I'm going to spoil it to you. It's about 32,000. This means that just for every 32 millivolts that the supply voltage starts to vary, the output voltage will only vary in 1 microvolt. How cool is that? Let's say you want to turn a huge signal into a small one. Then the microvolt variation is going to actually mess up with your data. So you should use a more specified amplifier, such as like an INA or any other instrumentation amplifier. CMRR, what's this? Why is it still on decibels? This one's a bit more complex, so I'm going to try my best to explain it to you. Here you have two signals. One is about 5 volts and the other one is about 3 volts. To explain the common mode rejection radio, you first need to know the definition of common mode voltage. The common mode voltage is determined as the mean between a group of signals, which in this case is about 4 volts. Understood? Great. But why is this so important? Due to errors during fabrication, amplifiers can actually amplify this one too. This is called a common mode voltage gain. This is how much they amplify these kind of voltages. Although the changes of this common mode voltage are small, again, small signals exist. Here's the simulation that shows how the circuit amplifies these two signals that have no common mode voltage, and this shows how much can the same circuit amplify these two signals that are completely common mode signals. In conclusion, CMRR compares how much does the circuit amplify differential voltage to how it amplifies common mode voltage. This relation for the LM741 it's about 96 decibels, which using the equation I just show you later, which using the equation I just showed you before, it's about 63,000, something like that, volt per volt. For the next specification, I want you to imagine this. Imagine a circuit that detects whether if a signal is higher than 4 volts. If so, an engine must be turned on. Here is, can the LM741 give up that current? Consult the datasheet if you want. And if that current is beyond 28 milliamps, well, you should consider changing your operational amplifier, or engine, or degree. And now, for my last trick, last but not least, I will be talking about what I consider the scariest part of operational amplifiers. The unforsaken offset voltage. I mean, you can be scared of something else, like women or getting robbed. Anyway, I feel this one's one of the most important, that is one of the first things you should look after in a datasheet. The offset voltage is a voltage that is generated after booting up the operational amplifier. It's just a tiny little piece of their DC. However, there's a big problem with this offset voltage. It gets amplified too. But not in the way common mode voltage gets amplified. No. This guy, it's exclusive. This guy, it's amplified due to the differential voltage gain. And this is so much of a big deal that LM741 manufacturers dedicate not 1 but 2 pins to solve this problem. To fathom a fraction of the chaos this little defect can make, imagine the situation. Let's say you're using an LM741 to amplify a little signal coming from space, because engineers can do whatever they want. However, the signal is about 0.3 millivolts high, so you amplify it. you take an inverting configuration with a gain of approximately 33,000, but at the moment of seeing the signal, you just see some distortion. Half of the signal is kind of lost. Well, given that the offset voltage of the LM741 is just about 1 millivolt, the output signal you have just amplified might just have 1 volt of amplitude, but 10 volts move upwards. For this situation, you have only 3 options. Number 1, use another op-amp, which is the money way. Number 2, think of something else to amplify the signal, like using individual transistors, but I'm not going to get into that. Or number 3, use the pins I just told you about, because that's the reason for existence. But well, that's about it. Nothing too complicated, right? Well, that gives us a lesson about how do electronics actually work. I hope you liked the video. I hope you cracked a few laughs, but most importantly, that you learned something. Goodbye.